Take 8. So, definitely go watch the Pretenders back on the chain gang, because that's what we're talking about, is the chain rule. So I think that it's definitely necessary this time to give myself motivation to get through. I've got candy corn for each page, not including the first page. And so hopefully that's enough candy corns. See, I have those candy corns ready. Ready are the candy corns. Okay, so the chain rule for Calc 1, remember, is for, how come that got so small? Composite functions. And so, you take the derivative of the outside times the derivative of the inside. For multivariable functions, that's what we're going to be looking at here in Calc 3. It's for when you have one dependent variable, two intermediate variables, and one independent variable. There's proofs in your book for when you increase the number of these. There's this proof too, and the number of those, and a similar idea. I realize that we haven't really looked at things that have one independent variable, two intermediate variables, and a dependent variable, independent variable. So I did want to look at this example 1 here. And if you were just given this question and you hadn't studied anything else, the natural response to this, if they're asking you to find dz dt, would be to look here, and we have z, we have x and y. They tell us what x and y is in terms of t here. And the natural question is, can I just plug that in right there and plug those things in right there and then take the derivative? And the answer is yes. That's what you can totally do. I'm going to put that over here because I want to show you that when we use the chain rule, you get the same answer. And of course, this is a really simple function. The functions get way more complicated, and so it's very, very necessary to use the chain rule. So this one you can do either. You can do either. And so this would be z equals, and then this is t squared plus 1 squared, plus, and, excuse me, no, it's minus. One of the takes was me making that same mistake, and all the other takes have been people calling me on the telephone because I'm so darn popular, and one of the mistakes was me not being careful with my FOIL. So I'm going to multiply this out, and I'm going to be careful to write it out and FOIL it. Yeah, Danny, I'm talking to you. You're the one that made me think that I could do the foiling in my head, and obviously I cannot. So t to the 4th plus t to the 2nd plus t to the 2nd plus 1. So this is t to the 4th plus 2t to the 2nd plus 1 minus, and then what am I going to have there? I'm going to FOIL this too. I'm not going to do it in my head, because when I try it in my head, I mess it up more of the time. There's people calling me again, texting me again. T to the 6th plus t to the 4th plus t to the 4th plus t to the 2nd. So when we, all of this is of course equal to z still. Try not to lose track of that. Now I'm distributing that negative, and yeah, I could combine the like terms. There's two of these, so minus t to the 6th minus 2t to the 4th minus t to the 2nd. Combining this up just a tiny bit more, I haven't taken the derivative yet, but I'm going to, minus t to the 6th. This is a simple example, and the algebra didn't get too bad. And so you can probably are noticing that, oh wow, if it wasn't simple and the algebra got bad, the algebra could really get bad. And it can. And so that's why we're going to look at the chain rule. And so this is minus t to the 4th. And here is plus t to the 2nd, and then plus 1. And I finally have got it as a z is the dependent variable and t is the independent variable. I'm trying to find dz dt. So here we go, dz dt equals negative 6t to the fifth minus 4t to the third plus 2t. And so voila, so we have our answer there. Okay, so now we're going to kind of discover here the chain rule just a little bit for when you have one dependent variable like we had and two intermediate variables like we had on that example and one independent variable. And this is not the proof. This is just kind of a hand wave idea of the proof. They do the proof in the book as well, and you can go look at more details. So it's just kind of just to give you the feel, just the flavor of how it goes. So let's say that z equals the function xy, and x and y are both functions of t. So that's what we've seen. And we know that for a small change in t, that x and y respond by changing. And these changes can be denoted delta t and delta x and delta y. Likewise, this causes changes in our height, delta z. And so now we're going to describe those changes in delta z. So delta z is the amount x changes z. So there's going to be two parts to how delta z changes. Because z was in terms of x and y, it's going to take into consideration the changes in x and also the changes in y. So how does x change z, and how does the amount that y changes z? And then remember that dz is a change in our height. And so I have that here and from our picture before, right? And so here is delta z, and it's the actual change in our height for small changes of x and y, so small changes in x and small changes in y. And we had said that you can approximate that with dz, right? So that was, a while ago. And so, and I just wanted you to remember that slope equals rise over run. And so that you can rewrite this as slope times run equals rise. And slope is another way of saying rate of change. So when we talk about the amount that x changes z, z is our rise, right? Our height change. Well, that's going to be a rate of change times our run, in this case, the amount that x changes. So delta z would be the rate of change in the x direction, right? So rate of change in the x direction times delta x. And then we have the amount that y changes. Well, that's the rate of change, slope. Rate of change in y direction times delta y. So we had notation, the partial of z with respect to x, right? We had notation for the rate of change in the x direction. And so delta z, the rate of change in the x direction, the notation for that is the partial of z with respect to x multiplied by delta x. And then we have the rate of change in the y direction. And I hope that you're already writing, that's the partial of z with respect to y. It's a partial. And multiplied by delta y. Then, on the next page, The pumpkins, the pumpkin treats are for when we get done with page 26. Then I will have a pumpkin treat, and that'll keep me going and keep me happy. I hope that you have some treats like that. I should probably start using not sugar for my treats. But anyway, if I divide everything by delta t, then I'm going to get delta z over delta t. And here the partial. And this is going to be delta x over delta t. And the partial. Oh, that's a y. That's a y. Don't forget I'm dividing by delta t there as well. Okay. And then if you find the limit as delta t goes to 0, so that's the next thing that we're going to look at. The limit as delta t as delta t goes to 0. That's partial. It started not looking like one. Now recall that this limit is equal to dz dt. And so this should have been delta t right there. And I was like, it's driving me crazy. And so this is equal to dz dt we had. And this partial doesn't have anything to do with delta t. And so it can be in the front. So that partial is going in the front. And likewise, the limit, just like this limit, was equal to dz dt. This limit is, what do you think? Dx dt. And the next one here, the partial can go in the front. And this limit here is dy dt. And then boom, we've done the chain rule. A little bit of hand waving here along. If you want to read more about it, certainly go read more about it. And anyway, so now we're going to give a try to doing this problem using the chain rule. I just summarized it right here for you. And we're going to use a tree diagram. And even though we're going to get more complicated chain rules, we're not going to build out another one. And you can go look in your book for all of them all built out. But, you know, as the variables change and those kind of things, it gets too complicated to have it like this. And, you know, and now they've changed the variable. Instead of z, it's w. And now I'm trying to follow that. And so here the tree diagram really helps you with that. So what you do is you put your dependent variable, and I'm going to try to put it over here, dependent variable, which is z, and then you put your intermediate variables, which are x and y. And I was taught to draw it on your side, x and y, and I know that the book draws it up and down, but it's the same idea. It doesn't matter. We're going to just be following the branches of the tree. And because I want to write it out horizontally like this, that's the reason that it's helpful to write it horizontally, and that's how I was taught to do it. And then x goes to t, right? And this is my independent variable. And you can have more than one independent variable. We'll do that. And you can have more than one. You can have more than two intermediate variables. So, and that's why having a chain rule memorized like this and not an idea of how you could find it on the tree, it's way more helpful on the tree. Now, I'm going to write out my plan, which will be the chain rule for the particular problem that I have involving the variables that I have. And if you don't do that, I can't give you partial credit if you get it wrong, because I have no idea what you're doing. And so I want to make sure that we write that out. So dz dt equals, because there is more than one intermediate variable, then this would be a partial. So the partial of z with respect to x times, and then we would continue on to t. And because there's only, there's from x to t, there's only one path. And so from z to t, we would have to go through those two, and that's why that's a partial. So this is dx dt, and it's not a partial. And then plus, well, we could have gone through y, so that's a partial here with respect to y, and then times, and then this is not a partial, dy dt. And then we're going to go pick up what each of these is equal to. And dz dt, the partial there, partial z with respect to x, there is 2x. Dx dt is 2t plus. And then here we have negative 2y. And then when we do this one, we have 3t squared plus t. And then just making it look a little bit nicer, dz dt here equals 4 and xt minus 6yt squared minus 2yt. So this is a good answer, and the book says it's okay to leave their answer there. And they give their answer often with x's and y's. It's also okay to go plug in the x's and y's. I don't. The only reason that I would do that is because I wanted to show you that, hey, you get the same answer as you got here. And so I am going to do that on this particular problem, but this is a good answer, and this is where the book stops. And so this would be if the book asked you this answer, this problem, this would be the book's answer. But I want to compare it to this, so that's the reason I'm going on. I know I'll get why did you go on? Do I have to go on? And the answer is no, you don't have to go on. For t, I'm going to write this as, and then x, just because it'll be easier for me, is equal to t squared plus 1. Minus 6t squared, and then y is equal to t cubed plus t. Minus 2t, and then y is equal to 2 cubed plus t. So that when I distribute this out, dz dt equals 4t to the third plus 4t minus 6t to the 5, the fifth, minus 6t to the fourth, and minus 2t to the fourth minus 2t to the second. So I'm almost there. Writing this one first, dz dt, not out of room yet on my paper, equals, so negative 6t to the fifth. I got the t to the thirds, this was a t to the third, sorry. Right there was a t to the third. When I multiplied that together, I got t to the fourth. I'm really tired. This is like the 8th time I've done this video, and I've got my phone on silent, and that's not enough of them. So where have I gone wrong? I have this right. I have that right. I now have this right. Minus, oh, right here. Oh, heavens, heavens. I know you were shouting at your screen right here. The derivative of t is not t. The derivative of t is equal to 1. Oh, have mercy. But I'm just going to live with it. I'm not going to start again. I have to do everything on one shot because I'm not much on editing. And it takes so long to edit just the putting it together. So we have that. So this was really not 2t. It wasn't matching. And I was like, but I'd give myself part credit because I wrote this out. And so I'm going to have part credit on this one. But I fixed it before the teacher came and graded it. And so I think I'm okay. So this is minus 2. And then y is t to the third plus t. And so how many algebra mistakes have I made now? Minus 2t to the third. That's the reason we want to stop here. Although I had a boo-boo there because of this. Okay, so here minus 2t. And then so hopefully now I have 4 minus 6 minus 2. That's minus 8. Plus 4 is minus 4t to the third. And then I have here 2t, so plus 2t. And like hot diggity dog, they do match one another. Again, let me reiterate, that's the book's answer, and that's where we're going to leave the rest of them. And so we did a lovely job on that. So we're going to try this example. Now, we've got some variable changes here on example 2. And so it's not just the regular chain rule. And so in order to get a chain rule so that we can use it out, we can use the tree. They help tremendously. I know that's a bad joke. Get it tremendously. I know it's terrible. I made that joke in class, and everyone laughed hysterically. They thought it was so funny, and I know they didn't laugh hysterically. Sorry. So now I've gone to lying as well, and so there's my tree. So my independent variable is w. My intermediate variables are x and y, and both x and y are in terms of t. Here they're asking me to find dw dt and evaluate that when t is 0, and that's a really, really lovely point. T is 0 there because you're going to notice that a lot of things just kind of go away. Did I earn this yet? Or was that boo-boo mean I don't earn that just quite yet? Okay, so dw dt, and then we would have a partial dw here, partial of w respect to x, and then dx dt, following the path, right, to get to t, plus, and then also to get to t would be here to y, so that's the partial. And you have a partial when it has more than one place to go. That's when it's a partial. So w has more than one place to go, but y only has one place to go, and so you have a full derivative there. Okay, so we're going to find these pieces and put them in, and then we're going to evaluate at t is at t is 0. So when you're going to see how to do that. It's going to be not so bad at all. And so we're going to have here, when we take this partial, y is a constant. So this y is just going to hold still. And then we take the derivative of x squared, which is 2x. And I'm just going to go ahead and leave it like that because I notice that some people are having trouble with their partial derivative. So y is a constant, so it holds still, y to the third. And then the derivative of the x, which is 1. And then dx dt, that's the derivative of the cosine of t, which is negative sine of t. And if I had a nickel for every time that a person did not put parentheses here and then treated it like it was a subtraction, I'd be so rich I would buy an island and live on it. I don't know, I get too lonely. And so I wouldn't probably buy an island because I'd have McDonald's for sure tomorrow. So anyway, so then when I take the partial with respect to y, so x is a constant, so x is just going to hold still, x squared, and the derivative of y is 1, and then minus, and then x is going to hold still because x is a constant, and the derivative of y cubed, which is 3y to the second, and then multiplied by the derivative here, which is e to the t. And I'm going to go ahead and put it in parentheses because I kind of feel like when I've done this that a person can follow what I have, that this one is here, this one is here, the plus sign, here's this one, and here's that one. And that gets me the most partial credit when people know what I've done. And so, and now I'm going to put in t is 0. And so when I go to put in t is 0, that part right there, sine of 0 is 0. So that actually wipes out all of that. And I'm going to let it wipe out that. I'm pretty tired. I'm not going to go figure out what that stuff is. But here e to the 0 is equal to 1. And so this is 1 times what we have here. And so you might be saying, but they didn't tell us what, they didn't tell us what x was, and they didn't tell us what y was. Well, they didn't, but we can find them, right? Because we know that t is 0. We know that x equals cosine of t, and cosine of 0 is equal to 1. So x is 1. And we know that y is equal to e to the t. And if t is 0, that's e to the 0, which is equal to 1. So y is 1. So now, when we plug this stuff in, dw, dt, right? This part, remember, all of this, it didn't matter what it was because this was 0, right? And so I'm not even going to go figure it out, noticing that. But this stuff, it does matter what this stuff is because this was 1. And so we'll put those things in. So here we get 1 minus 1 times 3 times 1 squared, right? That's a square root 2 there. But I can be kind of lazy on that. So that's 1 take away 3, which is negative 2. So this dw dt equals negative 2. So it worked out pretty lovely on the numbers. And so those were really good numbers there. Okay, so we're going to look at this next one, and this is just kind of a little bit of extending the concept of the chain rule. And already this one, I'm not so sure that I would have wanted to plug in that and have it squared and times that and have to do all of the product rule. Remember all the product rule that we would have to do. I mean, oh my gosh. And more of it here. And you notice by doing the partials, we didn't have to use the product rule. And so that saved us quite a bit of work. I think it would be way more difficult here to plug this in. Okay, anyway, the book convinced me of it. I'm convinced of it. So here we are on this next one. They're asking us to find dw dt. And we notice that instead of having 2 intermediate variables, there are 3. But there's still only 1 independent variable. So I'm going to make my little tree that helps tremendously. And so I'm going to have here x, I'm going to have here y, and I'm going to have here z. and then all of these are going to t. And so however you like to make this, I was taught to make it like that. If that's great for you, great. I noticed that your book, of course, I was taught, before, before this book was probably even, I think the guy was an author when I was a student, so maybe I'm being wrong on that. But the book shows that, and that's also fine. So it's whatever makes you happy on that. And so I'm okay with either of them. I'm also okay with you having your table like they have them in the book, which is on their side like this. Of course, they write the W this way and the X, Y, Z, and I'm okay with that as well. I think it's nice to have it on its side as opposed to up and down. That's how I was taught, and so it brings me comfort and happiness. This is like a football. It's almost football season too, which I don't know. I don't like football, so I don't know why I would care. So anyway, this is what gets you partial credit, is by writing carefully this out so that I know what your plan is on your derivatives. So this is going to be the partial with respect to x, and this is dx dt, and the partial, it's w not z, sorry, with respect to y, and that's a partial, and dy dt, and plus, believe it or not, that eraser thing made that drag. So here we're going to have the partial with respect to z times dz dt. So that's my plan of what derivatives I'm going to be taking. 3 partial derivatives and 2 regular derivatives. And the good news is that they don't require that I make everything in terms of t. And so I'm really grateful for that. I noticed that the Briggs book does, and so that made me really happy. I had voted for the Briggs book, and so it made me really happy that that my colleagues voted the Stewart book just for this one thing, because I mean that becomes such an algebra nightmare. So here I'm taking the partial with respect to x, and so these are little partials, and so this has x in here, and so fortunately this doesn't have x, so that's going to be 0 there, and so I had to remember. I said to myself, surely you remember that from Calc 2, and myself said, yeah, I kind of do. And so this is 1 over 1 plus xz squared. And then you take the derivative of this. And remember, we're taking the derivative with respect to x. So z is a constant. So you take the derivative of this, where z is a constant. So z is going to hold still because it's a constant. And then we're going to take the derivative of x, which is 1. And I'm going to clean that up. And then dx dt, so dx dt, that's nice, that's 1. Plus, and then the partial with respect to y. So this part, sorry, I hope that hasn't been up there a long time. So this part right here is no y in it. So that's a constant, right? X and z are constants, so that's 0. And then I have to write this as zy to the negative 1, otherwise I'll mess up the derivative. Now z is a constant, so z holds still, and then multiplied by negative 1 y to the negative 2. And yes, of course, you can, people ask me all the time, you show way more work than I do. Can I do that a little bit in my head? And the answer is certainly, but when you show more work, you can get more partial credit if you mess it up. And I find that when I show more work that I do less messing it up, although I've done plenty of messing it up, but you guys don't know what time it is, and I do. I'm not going to tell you it's bad, though. Anyway, so I'm really, really tired. So I'm giving myself the excuses. My grandpa used to say every time we go to play tennis together, because he always won, but he was worried that at some point I would be able to beat him as I was going through high school. So he would tell me on the way driving over there, he'd say, I'm on the antibiotics, and that I have a limp and all of the things that he had wrong with him. That way, if he lost, it was because of all these things. Anyway, oh, he was a funny old guy. Okay, so loved him, loved him, loved him. Now we're going to do the partial with respect to z. So this has a z in it. And so really, it's almost the same situation we had here. We were taking the partial with respect to x. And so do you guys agree that it would be just the same, except for what would be the one thing that would be different? So it would be exactly the same, except for, I hope you're shouting. Shout it out proud, except for it would be times x. And then plus, and then here, remember we're taking with respect to z, y is a constant, so this would be the derivative of z is 1, so this would be 1 over y. Times, and then, so that's cosh, that's sinh, so the derivative of that is cosh. And so other than making it look just a little bit nicer, which everybody always should make things look nicer, you should make things look as nice as you possibly can. So other than making it look a little bit nicer, like putting the z in the top would make it look a little bit nicer. So I want to make it look a little bit nicer without getting crazy. I don't want to write times 1. And here, all that negative and all that looks bad. And so I want to fix that up, the y to the second in the denominator and in the numerator. And in fact, I'm going to put the negative out here to the side. So I'm going to have negative right there. And so I put my negative there, and I'm going to have z and 2t in the numerator. So 2tz, and in the denominator y squared. So hopefully I haven't messed that up. And then plus, and then I can make this look just a tiny bit better. So x over, so I'm not getting crazy. I'm just cleaning it up to make it look just a little bit better. I'm not going to get a common denominator here or anything like that, just making it look a little bit better. And so there's our answer. And we're okay to leave it with x, y's, and z's and t's, and that's what your book does. So we did a lovely job on that. So that one was pretty good. I don't know if I messed anything up, if I should be allowed a pumpkin or not. And here, I had a little bit of problems with, I had been using the partial derivative font, and then somehow I chose a different one, but that is a partial derivative. I'll explain to you why it's a partial derivative right now. But this one here, extending the concept to have more independent variables. So our dependent variable is z, so I'm going to write that here. Our intermediate variables are x and y, so just 2 intermediate variables, but some of them have 3 in your book. And then x has 2 independent variables that build it. So there's u and there's v. And then the same here. There's u and there's v. So we are trying to find the dz du. And why that would be a partial is that at the end, there's not just one end, t. Remember and so there's choices to get there. So this is going to be a partial, and this is going to be a partial, and to get to the whole thing is a partial, because I would have, if I plugged in here, if I plugged in x here, I would have u and v. And if I plugged in y here, I would have u and v. So z is in terms of u and v, and not just in terms of t. So the reason that I didn't need a partial here at the beginning, so the reason I didn't need this to be a partial is that if I plugged in here for x, cosine of t, squared it, and out for y, e to the t, and here, and here again, all that, then I would have w in terms of only t. And so if I took the derivative of it, it would be just a regular derivative dw dt. So that's the reason. Whereas if I plug in here, x is u and v, y is u and v. And so if I wanted to take the derivative, I have two independent variables there. And so that would be a partial. So it would be a partial derivative. So that's the reason. Now, if somehow it extended, the concept extended more, and we knew what u was in terms of t and what v was in terms of t, then we could rewrite everything here in terms of t. Then we would be finding dz dt, and we wouldn't need partial. So that's the reason. Okay, so here we go. And like I said, I don't know on the font on that. I wanted to check on that. I'm just going to try to be happy. But I think I must have chosen, I don't know how that got going like that, and I didn't notice. And so this a little different deal there, but it's meant to be a partial, and I'm not exactly sure. So this is the partial of z with respect to x. And what am I supposed to be finding? U. So I'm supposed to be following the trail from z to x to u. And so this would be the partial of x with respect to u plus. And then now I'm following the trail from y. So that's the partial of z with respect to y times, and then following the trail to u. So this is a partial again because there's two choices there. And then now I've written out that partial derivative, and I'm going to find it. And I'm going to leave my answer in terms of u and v. And so this one is, oh gosh, it's not too bad. I'm so happy. 3x squared. And then this one is kind as well, 2u plus, and then this is 3y squared. And now every time I see variables next to each other, u and v next to one another, I think, oh, I'm going to have to use the product rule. But then I'm reminded, oh, if you're finding the partial, that means that's different than a full derivative. That means to treat v as a constant, because I'm trying to find du, right? Partial with respect to u. So if this is a constant, that would be 2v hold still times the derivative of u, which is 1. And so that's what's really nice, is that if you started plugging all this stuff in, I mean, it makes a mess. And so here, just cleaning it up just a little bit, just enough, that the people at UC Berkeley know that we know how to clean it up, just a tiny bit. And so I get that question all the time. Why do I not have to clean it up when I'm doing the AP exam, but I have to clean it up when I'm in community college? And the answer is because UC Berkeley loves us to have you clean it up. And so, and they don't love that the AP doesn't make you clean it up. I shouldn't be talking back. So got to clean it up just a little bit, not a lot. Okay, and then I'm trying to find this one here. It'll be my last one here for this problem here. So following the path, I'm going from z to x to v. So I'm going to follow my little path here. And I write out my path because I would like to get partial credit if I get it wrong. And I can't give you partial credit if I can't see what you were trying to do. And so this is your advertisement to me about what your chain rule, what the chain rule that you're going to use is. And So it's you saying, so that V. Okay. So I think this is going to work out okay too. I've got it where we can't see our problem. And so this one, now you notice that I already found that, right? I did that right here. And so I could look at where I've already done some stuff and I could use my work, particularly if it was a lot of work. This one wasn't a lot of work. So noticing I've already done that maybe is only good for verifying that I get the same thing both times. And so I had already done that. But I haven't done this. So this is 2v plus. I have done that. I did it. It was 3y squared. The only way that it's a work saver to notice that you've already done some of them and to use that work is if it was hard. And so at least this one wasn't too terribly bad. This time u is the constant, so this is 2u, and then times the derivative of v, which is 1. And then cleaning it up just a little bit because that makes this beautiful. There we have found both of them, and hot diggity dog. And so I'm going to write my little partial thing going here. Okay. And so the funny joke about the trees helping tremendously, and they definitely do. And you can imagine that if you started plugging everything that you know in, that you plugged in what x is into this, and you plugged in what y is into this, and you plugged in what z is into this, oh my goodness, there would be in the input to your arctan, there would be e's with not so nice exponents, and there would be cosines, and there would be so much product rule and chain rule that I don't think I could keep it straight if I went and tried it. Now, but what would I get if I plugged that all in? Would I get one variable, w equals one variable if I plugged it in? And the answer is no, I wouldn't. I would get w equals two variables, right? U and v. So we know that we're going to only be able to have partials here, or we'll be finding partials here. So writing out my tree, because they really help keep it all straight. And they're a way of getting what you're wanting to find. So we have x, we have our independent variable w, x, y, and z. X, y, and z. And then x is only in terms of u, and y is in terms only of v, and z is in terms of both u and v. Okay, so we've written out our tree, and we're supposed to find the partial of w with respect to u. So we're going to look at where we have u on the ends, and that's what we're going to be following through to. And so the partial of w with respect to u. And so there's no path through y that leads to u. There's only a path through x that leads to u. So I'm going to get that. So that's the partial, because there's three different choices with respect to x. And then from x to u that's the only place you can go. So that's a full derivative dx du plus, we don't need anything going through y, but we need something going through z. So that's the partial of w with respect to z times, and then the partial of z, because there's choices with respect to u. So that's my chain rule. That's not any chain rule written in your book. This came from my tree. My tree helped me write that chain rule. That's going to help me take this derivative. Hopefully I won't mess it up. And if I do mess it up, I'm still probably going to have the pumpkin. And so I'm going to allow myself the pumpkin even if I mess it up. which is very generous of me with myself. Okay, so right here, with respect to X, oh, software update, cancel. I hope, is that coming on your screen too? Enter your password to allow this, but I want to cancel. Okay, I don't know if that was coming on your screen or not, but I got a software update, and nothing can stop me now. I can't be software updating right now. Okay, so I'm looking here. Here's X. The tangent YZ, the arctangent YZ, that's a constant. And I'm trying to take the derivative with respect to X. So this is going to be equal to, I like to write my constant first. So this is my constant. And then I'm going to take the derivative of X, which is 1. So times 1. And I'm only writing that so that you can kind of see a habit of, I've been helping a lot of people with their partial derivatives, and they're having trouble finding them. And it takes practice. That's 14.3. It really does take a lot of practice. Now I'm taking the derivative with respect to u, which is 1 over 2 square root of u, plus. And then now I'm taking the derivative with respect to z. And so x now is my constant. So x will hold still. And then I remember the derivative of the arctan. I hope that you guys do too. It's 1 over this same darn thing squared here. 1 plus this same darn thing squared. And then what you're going to do is you're going to take the derivative of in here. Now, friends, we're taking the derivative with respect to z. And so the y is a constant, so times y, and the derivative of z is 1. And then, what, I almost look like a v. That's a y. Should be a y, right? Yes, should be a y. Because the derivative here, yes. Now we are taking, so that's that part. Ooh, mess. Okay, and then we're taking the derivative here with respect to u. So that means that v is a constant, and we're taking the derivative. I almost said the anti-integral. Oh my gosh, are you kidding? And that is I think it's correct though. Negative sign of u. And if I had a penny for every time, I said a nickel before, but I think it might be a penny, that a person did not put parentheses around that negative and then started treating it like a subtraction of sine of u, I'd be so rich that I didn't want the island because you remember that was going to make me lonely. But I wanted McDonald's, and I would bring all my friends to McDonald's. Why not? Maybe even I have had dinner, so I should not be talking this way. Okay, so I am cleaning up, right? Making it look a little bit nicer. And so you always make things look a little bit nicer. And so this negative on my sign is going to change this to be a negative right here because it's all multiply. So a negative right here. And what the heck, I'm going to put v up there in the top too. And I'll put sine of u up there in the top with it. Why not? And so that just kind of looks a little bit nicer. It's beautiful, in fact. I think it's tremendous, in fact. So we did a lovely job on that. Thank goodness that our book doesn't require that we now go and plug in all of the x's are square root of u, and all of the y's, so there was a x, and all of the y's are that, and all of the z's are that. Oh my gosh, they did. And so just to match the back of the book's answer, it wasn't like that at all. That would make me sad. And so I don't know if you remember implicit differentiation when you had it in Calc 1. It's been a while ago, but I'm sure that you used it some in Calc 2 as well. And this chain rule is a little bit of a different way of doing the implicit differentiation, but it works. It works just as well. So I'm going to show you that, and a little bit, not much of a proof on it, but just a little bit of a proof on it, just so that you can kind of see a little bit where it comes from. And so we kind of got our tree here. I kind of drew my tree out for you guys. And so in implicit differentiation, you have a function where x is a function of x and y is a function of x. And so I know the tree looks just a little bit funny there, but just to help us get kind of writing on that. And so this is what I have on that side of the equation. And so when I take the derivative, because it's just going to one variable here, x, this would be df dx equals, and then here df dx, and that would be a partial. So a partial here. And then here, and I'm going to just write this here going this way. And so this would be dx dx. And then plus, and then if I went this way, that would be the partial df here, partial of f with respect to y, times, and then here dy dx. That's not a partial. Okay, my little partials with their little hangers. I don't know, mine look kind of like backward sixes. So we talked about this in Calc 1, that, dx dx is just 1. And so right here we have just 1. Oh, and I forgot to take the derivative of the other side, which is 0. And then this is just 1. And if I want to solve for dy dx, that's what I always did, right? So when I go here and I'm going to put my finger over this, df dx is equal to 0, right? So if this is equal to 0 and I want to solve for dy dx, and this is equal to 1, should I write that? So I'm going to have this 1 here. So I would sort of subtract that to the other side. I didn't put my directions out here very well. And so that's a partial, this is not a partial. And so equals, and this is a partial, and it should be negative, and I'm going to have to get it better handwriting on it, or I'll get banned on YouTube for bad handwriting. And they'll take away my, what do people always get for 100,000 views? Gold star or something. They'll take away my gold star. I think I'd take away my gold star. I'm a star. That's not possible. So last but not least, I'm solving for dy dx. So I will divide by this. So dividing by this. And we had no notation that you loved more than this. So I have that negative. Don't forget this negative here. So I'm going to put this down here with a better notation. Do you guys remember the notation that we had for this? I hope you do. We loved it. The f with the little x meant the partial derivative of f with respect to x, and then divided by, and then here we're going to have that same thing. I told you guys that I've written out what we need to do, and then what I've written it in places where it's kind of in the way. I'll make a note, fix this. So, and then this is equal to the partial derivative of f with respect to y, as long as this is not equal to 0. So we're going to give a try to that. Now, the one thing we have to make sure of is how we started. You have to have 0 on one side. So you can get away with not putting 0 on one side as long as you have a constant only on the other side. But if you have other things other than that, you can't. And so I just want to say that's our habit, get 0 on one side. So they're asking me here to find dy dx. And we would have used implicit differentiation, and we would have done this by implicit differentiation in Calc 2. No problem. I wouldn't say Calc 1 because we didn't do E in Calc 1. But otherwise, we would have. And we would have had to do product rule right here between those two variables, which we won't have to do product rule when we do it by using partial derivatives, because you hold one of them constant. And so anyway, so it's going to turn, but it would turn out to have the same answer if you were willing to tediously simplify them both to the same. And so, but the same value definitely if you gave it values. So the first step, in order to use implicit differentiation to find dy dx, like we did in Calc 1 and Calc 2, but using partial derivatives, which we just learned here in Calc 3, is to get 0 on one side. So you have to chant that to yourself, 0 on one side, friend. And so I'm going to do that. So minus 6 and minus y e to the x squared equals 0. So I got 0 on one side. And then I want to take the partials. And so the partial with respect to, because I'm going to use this formula right here. And this was really bothering me. I mean, I know that we proved it out what it is, but I look at this and I would have been happier if it was y over x, but it's not. And so I'm grateful that I get a note sheet that I can write that on. And so, you know, I have to put it on my hand right here otherwise. Okay, so I'm going to find here the partial with respect to x. So this is 0 because y is a constant. The y is a constant for this term, so y to the third just holds still, times 2x, the derivative of x. 6 is a constant, so it's gone. Y is a constant, so I'm going to write it down, minus y. When you take the derivative of e for a variable, when your variable that you're taking the derivative of is in the exponent, then what you do is you write the e to the same darn thing down, and then you take the derivative of the exponent. People were asking me about that in class the other day, so I just want to reiterate that from your Calc 2 days. And so I think I want to make that look nicer right now. And so while I'm here, I'm going to make this look nicer. So this is 2x y to the third would look better. And I think minus 2x y e to the x squared would look just dandy. Okay, so we did a lovely job on that part of it. Now we're going to do the same here. We're going to find, and yeah, if you're asking, could I go back to the implicit differentiation section in Calc 1, and I know you had it in Calc 2 too, and can I do them this way, the problems that were there, and get the same answer? Yeah, if you're willing to simplify some, because it might be some more simplifying, but yeah, they would be equivalent answers, definitely. So now with respect to y, so this is 5y to the fourth. And here, remember, x is a constant. So I write the x down first, and then take the derivative of the y, which is 3y to the second. And then I was looking here, and I better make sure I'm here. And then the derivative is 0 for 6. And then we're taking the derivative with respect to y. And this is a constant. And so that's going to be 1, right? So this is going to be minus e to the x squared. I like to write the constant down first and then the derivative here times 1. Since I'm going to clean it up, I'm going to write it like that so that everyone knows that's what I did. And then I'm going to make this look just a tiny bit nicer. I don't know, it almost looks pretty good, but just a tiny bit nicer. And then I'm going to wrap these two things into my formula, right? And so it's kind of my habit. It's kind of nice. My habit is to find always x first and y second, the partial with respect to x and the partial with respect to y. And so almost it's already stacking them the way that they're stacked. So maybe that's a good way for me to say to myself, hey, I think I can do this. So don't forget the negative. And then you just stack these things. So we did a lovely job on that. Um, Man, am I so tired that it looks kind of dim. Now I've got a shadow on there from my lights. Got lights everywhere. Here, okay, we did a lovely job on that one. It's beautiful. And no, we're not done, but we're almost done. I didn't eat the pumpkins one at a time like I had intended. See, they're still all here. And if I eat that many at a short period of time, it might not be good. So anyway, extending the concept just a little bit for if you have more than two variables running around, and so if you do, and you can, I think the book probably proves it. I don't remember if they do or not, or if they just say by extension, hey, this is similar. But if I'm trying to take the partial of z with respect to x, that's going to be negative of the partial of x over the partial of z. And if I'm trying to find the partial of z with respect to the partial of y, that is the partial of y over the partial of z minus of it. Okay, so we're going to try that, but remember 0 on one side. That was the part that you have to be really, really, really careful of. So here we're going to have yz. Well, maybe I'll put the, it doesn't matter. Oh, then I'll get different signs than when I did it last night, or whenever I solved the notes. And if I do it differently, then people will say, but the notes that you posted are different. And so I could have gone the other way, and my signs would all come out in the wash. And but I'm not going to do it. I'm going to go this way. So let's see. When was I asked to find both of them? Are you kidding me? Okay, so I'm going to find this one, I need this and this. So I'm going to find that. And so this doesn't have an x in it, so it's 0. And this does have an x in it. So I remember, so I have 1 over negative, because it's negative, 1 over, and then x plus z. And then you need to take the derivative with respect to x of the inside here, which is 1. So times 1, right? And the derivative of z is 0. So that is our derivative here. I'm just going to erase the 1 and not write it again. But I was kind of thinking that way. And then now I'm going to do, I need fz, and it's going to be my habit, partial with respect to z, to stack them like that. And so that I'm kind of using my formula. So this is what the habit I'm going to try to develop with myself that I just decided was a good habit. I didn't do it on my notes over there, but, didn't do it. I didn't do it on these notes, but I'm trying to develop this habit now. Okay, with respect to z, so y is a constant. So, and Miss Donna, you need to get down here. Don't look at that anymore. I'll put my eraser over it so I don't look at it again. And so y is a constant, so I like to write it first, times 1. And then I'm trying to take the derivative with respect to y, and with respect to z, with respect to z. So z is right here, so it's minus 1 over x plus z, and then the derivative of z times 1. And I'm just going to allow myself to erase these ones, right, on my thinking about the chain rule. And so there's that derivative. Just lovely. And so then we were supposed to find here the partial of z with respect to x, and that's equal to the negative of, and then I have this negative 1 over x plus z, and then y minus 1 over x plus z. And that's not okay for us to leave something looking that nasty. And so, but all we have to do in order to make it look nicer, all we have to do is to multiply by x plus z. And so I'm going to do that. I've got 3 terms, right? And so I've got, and do you guys agree that these negatives right here are positive? Is that okay? So I've got this term here, and when I multiply it by x plus z, I'm going to multiply that term by x plus z, I'm going to multiply that term by x plus z. So I'm going to be multiplying all 3 of these, by x plus z. And so when I do that, here in the numerator, I just get 1. Remember, this made a positive. So 1 in the numerator, y times x plus z. And then here I'm going to get, when I multiply by x plus z, the x plus z's are going to cancel, and I'm going to get minus 1. And now I don't have a complex fraction, and so to me that's a good answer. It's also a good answer to distribute the y down there. If you wanted to, you could distribute the y, and that would also be a good answer. And so, so we did a lovely job on that. And I'm going to come over here and draw my little line. They also asked me to find the partial of z with respect to x. So partial of z with respect to x. And so, I'm going to find the pieces I need first, and I'm going to stack them. So I need this, and so I haven't found that yet. And good news, I have found the other, right? So I'm going to write that out, and that actually turns out nice. Remember, I'm putting my eraser on that so I don't forget. So y is what I'm taking the derivative with respect to, and z is a constant. So I would write z down, and I would take the derivative of y, which is 1. This does not have a y in it, so hot diggity dog. So the answer is just the partial with respect to y is just z. And then now, this other one right here, I have it from here, and so you don't have to write it again if you don't want to, but I am going to write it because I have a new lovely habit, which is you just stack these with a minus. And so that I feel like I've written out my formula. It's always a good idea on your test to write out what formula you're going to use, because sometimes I can't even figure out what formula a person is using. And so it's really hard to give partial credit when you're just like, where did this stuff come from? I'm not even sure, because it's not, there's some piece of it that's not right. And so same thing, multiplying all of my pieces here, here, and here by x plus z. So that same thing, because you can't have a complex fraction. Running around with a complex fraction is definitely a no-no on the, hey, make it look a little nicer zone. I'm going to make this one look a lot more like a partial than I did when I first wrote it. So the minus out here in the front, and here I'm going to have z times x plus z. And here I'm going to have y times x plus z. And then here I'm going to have minus 1. And, oh, yay, 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 yay. Okay, so that's very good, very good. And that's all. That's all I have to say. Nothing more to say. I hope I had this recording. If this is not recording, tears will come to me at this point. Okay,